Hello everyone, and welcome back to Solid State Physics in a Nutshell, brought to you by the Physics Department at the Colorado School of Mines. My name's Eric.
And I'm Nicole.
Our description of lattice vibrations so far has been fairly classical and hasn't involved any quantum mechanics. Today our goal is to introduce the quantization of vibrations through quasi-particles called phonons.
How to describe phonons can seem a bit tricky. We're talking about vibrations, but we're describing them as quasi-particles.
The old wave-particle duality.
I find it best to compare phonons to stuff I already know, like photons and quantum harmonic oscillators. In early videos, we invoked that the vibrations in a lattice behaved like harmonic oscillators.
And the energy of a particular mode for a harmonic oscillator is given as U is n plus a half h bar omega, where omega is the frequency of the oscillation, and n in this case would be the population of the phonons in a particular mode of wave vector q.
On the other hand, phonons also behave like photons. Both are bosons, so multiple states of the same energy can exist in a given system. Also like photons, the amplitude of vibrations in the lattice is related to n, the number of phonons with a particular wave vector q.
We can actually prove this by looking at the kinetic energy density in our system. Instead of the exponential, we'll use the simpler form for u, just using cosines. Plugging that into our kinetic energy expression, taking an integral over the crystal volume V, and looking at the time average, we get an expression for the total kinetic energy in terms of mass, omega, and amplitude.
For a harmonic oscillator, the total energy for a particular vibrational mode is divided evenly between kinetic and potential energy, giving us half the total energy for our kinetic energy.
So then if we set these two expressions for kinetic energy equal, we can then move some stuff around and get a relationship between the amplitude and the square root of the phonon population, n.
Cool. So more phonons of a particular q means that mode has greater amplitude.
This brings us to part 2 of this screencast, looking at how phonons carry no linear momentum.
None?
Nope, and that's why we call phonons quasi-particles. They'll interact with other particles as if they're carrying momentum, but they don't actually have momentum. It's sort of analogous to oscillating atoms in the hydrogen molecule. They have kinetic energy because of the oscillations, but the center of mass of the hydrogen molecule doesn't move.
That analogy seems like a standing wave solution when we've been treating our displacement as a traveling wave.
Right, but if you zoom out of it and look at the crystal, does the center of mass move for vibrations?
No.
Yeah, although we have individual atoms oscillating, over a time average we get no net displacement for the crystal's center of mass.
While that makes sense, I'd like to see some math to back that up.
Sure. Let's start with P equals mv, where we add up all the displacements over n before taking the time derivative. This time we'll use the complex exponential form of u sub n. While this looks a little ugly, we can simplify it using this infinite series approximation.
That doesn't look much better.
Not quite done yet. First we need a boundary condition on q, which we'll go through in the next video, but for convenience I'm just going to invoke it now.
Okay, so let's plug that into our new momentum expression, and this exponential in the numerator will always be 1 since n is an integer, and we get 1 minus 1 in the numerator.
Which proves mathematically that phonons carry no linear momentum. This looks like a good place to stop today. Nicole, why don't you walk us through a recap?
Yeah, so first we introduced the term phonons to describe vibrations in a crystal. By analogy, we know that photons are bosons that can reside in the same mode to increase the amplitude of the light wave. Phonons do the same thing, but for vibrations in a crystal.
Phonons also act like simple harmonic oscillators in that the energy of a vibrational mode is n plus a half h bar omega, where n is the phonon population in that mode.
In part 2, we learned why phonons have kinetic energy, but no linear momentum.
So it's a little creepy that phonons aren't real particles. The wave vector q is less physical than the wave vector k for photons, which is consistent with being able to shift q by the reciprocal lattice vectors.
Before we go, here are some questions for you to consider at home. First, I talked earlier about how for harmonic oscillators, the total U is split evenly between the kinetic energy and the potential energy of our system. Where are each of these energies represented?
I also stated as a fact that phonons act like they have momentum when they interact with other particles. Physically, why are phonons able to do that? Next time, we're going to take a look at how phonons behave in a finite solid. Okay, that about wraps it up for today. Thanks for watching Solid State Physics in a Nutshell. See you next time.